People who are interested in finite elements get enthralled with the equations that describe the system, and since this is a large set of equations, typically 5 to 50,000 degrees of freedom, it seems to be a dominant aspect of the total picture. In fact, though, it's the modification of the equations prior to solution that's really important and where the real engineering comes in. So I've packaged together some of these methods and put them in a lecture called Modification of Equations. To some people this might seem a little strange as to why I worry about this, but it is the real finite element theory that's exemplified by these methods. First we'll start with a description chronologically of the solution process. This leads to the creation of a standard form where all of the unknowns are on one side of the equation and the knowns are on the other. And then I go into a series of things that must be separately considered in the setting up of the finite element problem. And these are really important topics that distinguish between the casual user and the expert user. We'll have a problem session at the end. Let's now talk about the solution process, where we'll follow the logic that the finite element analyst might use. This could be a little different than the logic that a modeler might use working on a screen, or that a mathematician might use. I think I'd like to follow, indeed, the chronological order in which the finite element code itself will, in most codes, remove variables, clean up the problem, and organize it into the optimum standard form. Generally, we start with a set of equations shown at the top here in the linear static form. Many finite element laws are like this, even including frequency response in dynamics, where the stiffness matrix might be a function of a forcing frequency. But generally, this is a set of linear equations, and we're interested in the static case. Now, what will happen first is that the multipoint constraints that have been imposed on the problem should be first carefully considered, and this generally removes a degree of freedom for every multipoint constraint. We'll talk about those in a few minutes. Then the single point constraints are removed. This will take a pretty big chunk out of the problem size. You might see on the right here I've shown, perhaps with a 50,000 degree of freedom problem, that you might remove only, say, 50 degrees of freedom due to multipoint constraints. On the other hand, it's quite common for 10% of the degrees of freedom to be removed by the single point constraint list. And these would be the normal boundary conditions where the body is being held fixed to the ground. Following that, it's still the analyst's obligation to remove any remaining rigid body modes. And these are the ones that would allow the body to move around in space and cause a singular stiffness matrix. That will, in general, remove as many as 6 more degrees of freedom, but not a big reduction. Then, having the equations in somewhat of a standard form here, notice that I have the red color here for the displacements that are unknown, and they are now organized on one side of the equation and the forces on the other. At this point, you worry about optimization and whether you need to resequence the degrees of freedom to minimize bandwidth or wavefront. Once that's done, you can then solve the problem, and although I show here a symbolic inversion, in fact the body, the stiffness is not really inverted, but rather is handled by what is called triangular factorization. So this is a nice symbolic way to think about solution, but in fact isn't done that way. Then when the solution for displacements is finally found, you can then recover forces. You can recover forces of constraint, internal element forces, bending moments, this sort of thing, membrane stresses, interior stresses, strains, and any other detailed information. This recovery step need not be done, in fact, if it isn't necessary, but is in typical problems. Now let's concentrate on this standard form. The standard form has all the unknowns on one side of the equation and all the knowns on the other, as shown here. This desired form is one where the forces are known and then the unknown displacement, shown here in red to attract your attention, are all on the left. Now, furthermore, you would like for the ideal problem for the stiffness K to be real, symmetric, and positive definite. This will imply a stable structure that can give a response under a given loading condition. Now, unfortunately, the original statement of such a problem generally is not in this standard form, but rather is in a mixed boundary value form shown below. And this is where you have some of the displacements as unknowns, but some of the forces as unknowns. I show a non-homogeneous displacement condition here. That is a non-zero value of 4 units in the third displacement component. That means that the engineer doesn't know the reaction force over here, or force of constraint that's imposing that displacement. And this problem in this mixed form is difficult to handle, so we have to straighten that out. I'll repeat the mixed boundary value problem that I had at the bottom of the previous figure here, so that we can refer to it when we look at our reduction method here. First of all, one of the most efficient ways to handle this problem is by partitioning. Interestingly, partitioning isn't discussed much in textbooks, and yet it's the way that you can remove those prescribed degrees of freedom and then efficiently solve the rest of the problem. I show that here where the third equation appears below, and once the 2x2 problem has been solved, then the solution for the reaction force, or so-called force of constraint, would be a forward multiplication leading in this direction to the force of constraint. In order to do this partitioning, though, you must account for the terms that have been removed of the form 1 times 4 in the first equation, which is shown subtracted off, and then 2 times 4 in the second equation, also subtracted off. So the penalty that you pay for partitioning is a certain amount of bookkeeping in keeping track of which degrees of freedom have been removed, and then a certain amount of updating of this vector on the right side. Notice that if it had been a homogeneous boundary condition, which is by far the most common, with a zero displacement imposed, then you don't get these correction terms because they drop out. They're identically zero. Now, for small computer programs, and you'll see this sometimes taught by teachers in college classes, that you would rather not go through the partitioning, because if the prescribed displacements are sprinkled throughout the structure, you get into Boolean algebra where you have to really bookkeep on which ones are now gone and which ones are remaining. A way around that would be to carry that equation where the displacement has been prescribed in a trivial way. So you carry along trivial equation, but doesn't require renumbering. In this case, you put a unit value in the coefficient matrix on the diagonal. You put zeros in the rows and columns that correspond to that dominant term, and then you put the enforced value on the right-hand side. This also requires that you correct the load vector, and you get an apparent external load here due to that known degree of freedom in the remaining coordinates. Again, though, relatively easy to do for homogeneous displacement conditions where you force displacement to be zero, because then these would drop out again. The nice thing about this is then that you don't have to do the work of the Boolean algebra to keep track of your mapping of your old coordinate set and your new coordinate set and the relation between them. Rather, you solve again an n by n set of matrix equations here, whereas previously you had something less than that. There is another way to solve these equations in the original number so that you don't require renumbering your entire set of variables. This is called a penalty approach, and again you pretend that you don't know what this value of the enforced displacement was, and if its value was to have been 4, you put that over here in the load vector, you carry along the coefficient of that term on the main diagonal, which is good from a standpoint of scaling that we'll think about in a minute. And then you multiply that term by 10 to the 8th, both on the force over here and on the coefficient here. Now what you have just done is to put a rather large number here that will drive this supposedly unknown displacement, although we really know what it is, to take this value of 4. Because you see, if the 7 is scaled of roughly the same size as the other terms in the equation, and we do have pretty much diagonal dominant terms in the finite element method, then this 10 to the 8th will mean that we will overwhelm the other terms. The third equation will basically say that U3 equals 4. There will be some slight error in that, and it can be driven out by raising the exponent to higher and higher powers. This same method is used in linear programming. I know years ago I taught a method called the big M method, and the big M was a big multiplier. See, that multiplier is the punishing, it's the penalty that will not allow the known displacement U3 to vary much from its prescribed value. Lastly, one could use Lagrange multipliers in such an attempt to solve these equations. Again, you might pretend that you didn't know this displacement and leave the equation as it stands here. Then you would have to add an equation that would prescribe this condition, and with a Lagrange multiplier that would again penalize you if this were not true, and that Lagrange multiplier can take values which can have physical interpretation. But in any event, rather than solving the n by n set of equations, this time you solve more. In fact, as many more as you have constraints. So this method in linear problems hasn't been as popular as the others, but apparently has some advantage in nonlinear problems, and you hear quite a bit about it in contact problems. Now let's look at several of the methods that are used to modify the equations of equilibrium. It's a bit of a shopping list, and I'm going to present them roughly in the order in which they're done chronologically within the finite element codes, but the ordering really doesn't matter. We're going to start out with multipoint constraints. Multipoint constraints are a linear homogeneous relation between two or more coordinates. And these might be really at different nodal points, but on the other hand, it might be two coordinates at the same node, such as I've shown in the example below. It's interesting that the standard form is homogeneous. That means with a zero right-hand side. However, this equation can be converted into non-homogeneous form by using perhaps a scalar variable here for one of the degrees of freedom and then constraining it to take a specified value. So you could build a constant into this. This factor Rj is a coefficient, and there will be such a weighting coefficient on every one of the degrees of freedom. A typical convention is to remove the first degree of freedom in this list in favor of the others. So because it is a single algebraic equation, you can use it to remove one degree of freedom. I'm going to show an example here where we might use just a single multipoint constraint. For instance, if you had an inclined plane as shown here, and a body that was constrained to slide up and down it on this little cart, this wheeled cart, then you'd find that your degrees of freedom must move in this prescribed way, where U21 would have to equal U22. To put it in the form above, you would write it as so, with a positive 1 coefficient on U21 and a minus 1 coefficient on U22, setting it to be 0. So you can see how you can force such a simple system into such an equation. The multipoint constraint relation, however, is more complicated than you might think at first. Some years back, I had been using these, and then I discovered at a point that I really didn't understand what I was doing. And here's why. If you take a single example of a multipoint constraint, one equation involving several variables. Let's suppose we take that previous one with U21 and U22 and then the force F21 and F22. You'll find that when you use that single relation, that the variable U21 will disappear from the variable list in typical codes and be replaced by other components. But what you have done really is presume a value of one of these two displacements, and you haven't specified anything about the forces. So, although it might be interesting to think you could get away with prescribing one equation and eliminating both the force and the displacement, there's something illogical about that, and that's what caught me. Well, the answer is that when you specify such a multipoint constraint between the degrees of freedom on this side of the equation, simultaneously and hidden to the user, within the finite element code is imposed a condition that the forces do not do any work. In other words, it's a workless constraint, or a holonomic constraint, as the dynamicists say. And that equation is shown here, namely that the displacement must be orthogonal to the force. So in our case, if the forces over here are in red and the displacements are in blue, we've already constrained the displacements to run along this axis. Then, as a separate condition, it's required that the forces be perpendicular. And that means you have a workless constraint force. That can be written out in vector form shown here. And that is done for the user without any comment in typical codes. And so be aware of that at some point, that in fact for every displacement constraint appearing as a multipoint constraint, there is a hidden force relation that makes the constraint workless. Let's now consider symmetries that can occur in physical systems. I think we're all aware that there are reflective planes in many vehicles. There are cases where you have rotational symmetry about an axis. So we'll consider these as a form of modification of the equations. Some of them lead to single point constraints, some of them lead to multi-point constraints. We'll start with the reflective symmetry shown here, which is for an aircraft with a vertical reflective plane through the fuselage. And this is a useful concept when one has a plane of reflective symmetry in geometry, material, and displacement boundary conditions. But you do not have to have symmetry in the loading. That can be general. Let's call it asymmetric loading. And the procedure is to break the problem into symmetric loading and antisymmetric loading, and then sum the two results. So let's look at this wing with a set of symmetric loads on it and a separate set of antisymmetric loads. The symmetric loads are those to the back, drag loads, and those are mirror images of each other and therefore symmetric. These rolling loads, one down and one up, appear in the opposite sense that a symmetric pair would, and so we call those antisymmetric loads. You can always resolve a question of whether loads are symmetric or not by indeed doing a mental experiment of putting a mirror at this reflective plane and then imagining what the image of this reflected load in the right half would look like. If that corresponds with what is truly on the left half, then you have a symmetric case. If it's opposite, then you have the antisymmetric case. If it's a combination, then you have to break your loads down further. Now, the way that this is handled, this is a traditional sort of breakdown of a problem into a symmetric load and set of boundary conditions and an antisymmetric load and set of boundary conditions. And then these two are added up to give the total solution. This might seem suspicious in as much as you're solving two physical problems with different boundary conditions, but these really aren't free boundary conditions. These are cut planes that are exposing what's happening in the interior of the body, and this process is anticipating what would happen over the complete wing were it completely symmetric and then were it completely antisymmetric. So it is technically correct, of course. Another kind of symmetry is called rotational symmetry or cyclic symmetry, and this has to do with bodies that have symmetry about an axis. Here I show a body with two regions. You could use the cross-hatched red region to replicate the other region, but merely by rotating it about that center axis. Here's a three-segmented pinwheel that can likewise be swept out in that same way, and the segments are spaced 120 degrees apart. Here's a solid body that shows that this is really a three-dimensional concept. It turns out the axis must be straight, and again you can rotate this fundamental region in the other three positions and create the rest of the body. The interesting thing about this form of symmetry is that you only need to model the cross-hatched fundamental region. You get conditions at the cut edges that are governed by multipoint constraints. In other words, the displacement, say, at that point must be related to the ones over here when you use cylindrical coordinates. So cylindrical coordinates are an integral part of this theory. It's really kind of an elegant theory. It's in the Nastran codes and others by now. Richard McNeil did a lot of the development on this, and I find it a very fascinating field. It's not used a lot in practice because perhaps because of the lagging on the graphics packages that often they can't represent the results on the fully assembled body when you get them. But as a technical way to reduce the size of a problem, it's really wonderful and will save you occasionally when you can't get your given problem on the computer size that you have available. There's also a kind of symmetry that's a combination of reflective and rotational symmetry. It's called dihedral symmetry. Here you have perhaps a cartridge chamber or a hydraulic pump, as I have helped model, and you have holes that are periodically spaced around the central axis. But there are reflective planes of symmetry throughout here. In fact, there are apparently 4 of them. And you can subdivide this body into even smaller segments, such as this cross-hatched one, which, if you first reflected it, would give the other part of this region. And then together, if you rotated that combined region around 4 times around the axis, you sweep out the whole body. So this is an interesting kind of symmetry. Translational symmetry, shown below, is basically a lattice type of symmetry where a pattern is repeated on straight lines. The example I'm showing here is basically a bandsaw blade that's cutting through a really thick log. As a result, we might postulate that it is getting the same loading on a number of teeth at the same spot, although my sketch will be a little bit shaky. And therefore, the engineer can postulate that if you isolate one segment of this blade, then whatever is happening at one node on the boundary to the right will have to be the same as what happens on the node at the same position on the left. And so you can make kind of a homemade symmetry from those arguments. You still have to remove what are called rigid body modes, which we'll discuss later. So just making sure that this thing works in a periodic way isn't the whole answer, and there's even further modification to be done. Aksi Symmetry is a kind of symmetry that's often seen in lathe pieces and other bodies of revolution. Again, you need a straight axis of revolution. The body is swept out then by rotation of one surface, such as shown here in the cross-hatched view. And it is possible to have skew in this. I've never done such a problem, but you can account for that. More often, though, people are dealing with bodies that are either shell-like surfaces of revolution or solids of one material. When we discuss the reflective plane, I mentioned how the engineer must create symmetric and antisymmetric boundary conditions at that cut reflective plane. And that's an important enough topic to devote a section to here in our lecture. So we will look at those boundary conditions, and it's a solved problem and something that you can more or less tabulate the answers and have them forever, but you need to go through this once. I'll start out with what are called elasticity elements, and these are solid bodies that only have the translational degrees of freedom. If I show you such a body here that has been aligned in a way that there's a reflective vertical plane, and then I just by coincidence have shown symmetric loads on it, then the engineer would attempt to model half of that and put symmetric conditions on this cut reflective plane. Now, I've shown a model for the boundary conditions as a set of rollers, and that's not obvious at first, but it will turn out that the reflective plane has that kind of physical interpretation, as if it were a greased surface or a sliding surface on rollers like that. We'll discuss that in the next figure. We'll look at this body in the entirety to see if we can infer what the conditions at its center line or its reflected plane should be. Here I show symmetric loading on such a body, and the reflective plane would go through here. It's really through the plane formed by the 2 and 3 directions. First of all, we might say that because of this balance of forces horizontally, we wouldn't expect the body to move either right or left, and at the center line at that plane of symmetry, we would expect the translation in the one direction to be 0. Secondly, if we look at these vertical forces here, we would realize that they will not have the ability to act against each other at this center line. They're headed in the same direction and they don't oppose. Therefore, there shouldn't be any shear force F3 if we were to cut that body at that point. And lastly, you would get the same effect by looking down from above in the 2 direction and would come up with this 0 force condition. Now, when you want to find the antisymmetric boundary conditions, by far the easiest thing to do is to just take the complement of the symmetric conditions. So for instance, instead of T1, the translation in the one direction being 0, we know that it's the force in the one direction that's 0. Instead of the forces in the 2 and 3, it's the translations in the 2 and 3. So it's a change, I would call this the complementary conditions that occurs. You can argue these with some difficulty. For instance, on the first one, if we try to argue from first principles, if this force were horizontal and this one were horizontal, the question is, and if you cut a plane, can they act against each other to cause some net force across that middle? And the answer is no, that they both act in the same direction. So that argument is comparable to the one that we used earlier for these vertical forces over here. But the going gets tougher, and when you get into what are called elasticity, what are called structural elements, which I'll get to next, then you find that that's a difficult task, and I would rather rely on the complement of the symmetric case. Let's now consider structural elements. These are the ones that can carry moments and will support angular motion, as well as the translational motion. Here is a flat plate-like body that has a reflective plane through its center, the green plane. I show some asymmetric loads on it. And the question is, if we were to divide this problem into a symmetric and an antisymmetric part, what would the boundary conditions be at the cut plane? Well, we've really already figured out the translational quantities, so the only new thing would be the rotational ones. Over here we also know these translational quantities. So we're in pretty good shape on that, but the moments and angles are what we don't know. Well, let's think about this. If we were to look at rotations about this degree of freedom 1, to have mirror image moments about that, you would have a moment about this axis in this direction, and on the back side a moment that would have to also go in that same direction, you see. And the question is then, at the center point, could you have internally one of these acting against the other? And the answer is no, that since they're in the same direction, they can't support, or they won't cause any internal moment like that. And so the moment about axis 1 is 0. If we look at this body from the top view and consider symmetric bending, it should be of this nature. And we would realize that on the reflective plane there really shouldn't be any net rotation about a vertical axis there, and that would be the third direction, so rotation about the 3 axis should be 0. Likewise, on a front view, if we would look at it, we would hope to see symmetric bending like this with 0 slope about the 2 axis. So we can rather quickly determine the symmetric conditions. And then the antisymmetric conditions over here will be the complement, where there was a moment on the left, moment about 1, we'll say the rotation about 1 is 0 on the antisymmetric case. And then where there were 2 rotations, there become 2 moments to be 0. I have a friend, Subhash Kelkar, who has a little rule of thumb on this, which some people might find helpful, and it is that the symmetric problem under elastic deformation, if the reflective plane were firmly attached to the wing, it would tend to stay in the same plane. And so all of these conditions tend to keep that reflective plane where it is. Although it can slide and rotate within its own plane, it cannot bend away from that initial plane. And whereas the antisymmetric boundary conditions do that, in fact, they allow such moving away from the initial reflective plane. So that's an interesting alternate viewpoint. Let's change now and talk a little bit about rigid body modes. Rigid body modes are a unique phenomenon that happens in bodies where the body can translate or rotate without causing any strain energy. As a result, you might say the body is very weak under that kind of a displacement field because it can happen at will and typically with arbitrary amplitude. Now, unless this is handled, it tends to destroy a stress calculation because the stiffness matrix becomes singular. This means that the determinant is 0. And then you cannot do the solution process. There's a sub-case of this which can be handled. It's called inertia relief, and it is installed in the Nastran programs and probably others, where an unbalanced force on a structure can indeed be equilibrated by reversed effective acceleration forces, D'Alembert forces. That's a special capability. I would probably view that as an advanced topic. So for the average practitioner, rigid body modes are an evil to be overcome as soon as possible. Let's consider a body in 3 dimensions, such as an airplane. This airplane can undergo the rotational motions such as roll, pitch, and yaw, and also can do translational motions such as plunging up and down. So any three-dimensional body embedded in a three-dimensional space has that possibility. So you must consider those 6 rigid body modes. There are a lot of physical problems where the problem is initially envisioned as being captured in a reduced dimension space. We have names for those: two-dimensional problems, Aksi Symmetry, plane stress, plane strain, and line elements that are constrained to slide upon a line. A physical example would be this telephone that's constrained to slide on a desk. Now, when you do such a reduction of a problem at the outset, then the remaining number of rigid body modes is severely affected. For instance, a telephone to slide on a desk can only translate in 2 directions and can rotate about a vertical axis. So you do get 3 rigid body modes remaining in such a system. There's a minor refinement that if the receiver were to fall onto the table and skitter around, then it too could have rigid body modes. And depending on whether it were allowed to roll or tumble, it might have even as many as all 6 of the original rigid body modes for a body in 3-dimensional space. A more restricted case would be a dial phone where the spring in the dial mechanism had broken, and then you get a rotary degree of freedom. That's called a mechanism, and we'll talk about that in a little bit. If a body is constrained to lie symmetrically about an axis, and if the loads are also symmetric about that axis, then you have the case of Aksi Symmetry. This is a rather special case, and the reason is that any such finite element modeling such a body is really a ring element that extends around the axis of symmetry. And so that any motion of that element outward would create hoop stress. Likewise, any rotation of such a body, if we have this entire meshed ring body here, if it were to be rotated to any extent,